Day 162, homework hints, honors physics, photoelectric effect, de Broglie wavelength. Here we have monochromatic light with the threshold for emission from platinum. Now you need to know the work function for platinum. I looked that up. For platinum is PT, I believe. The work function is it's about 6.4 electron volts. And then for barium, the work function, it's 2.5 electron volts. Basic idea in this problem is the photoelectric effect equation, E of an incoming photon, the energy, equals the work function for the particular surface plus the maximum kinetic energy of the photo-emitted electrons. So in this case, what they're telling you is, you read the problem, you have incoming photons of 6.4 electron volts. So the initial setup here is 6.4 electron volts for the monochromatic light of that energy for platinum, equals now these particular photons are hitting the barium surface, which takes 2.5 electron volts of energy to loosen those electrons, so to speak, plus the extra energy left over goes to the kinetic energy of the electrons. Bottom line is, you solve this now for the kinetic energy of the electrons. This will be in electron volts, but when you go to the kinetic energy formula, that's always in joules, so you have to convert the answer to this first step to joules, and then simply plug that answer in for the kinetic energy in the kinetic energy formula, Ke equals 1/2 mv squared, so your answer from this problem goes here, convert it to joules first, and using the mass of the electron as 9.11 times 10 to the negative 31st kilograms. Alright, let's skip to problem 13. 12 is pretty straightforward. Alright, finding the momentum of photons. Looking back to problem 6, there's extra information there, basically the data that you need. But we'll essentially be using this equation, lambda equals h over p, the de Broglie wavelength equation. And as a reminder, you cannot use p equals mv for photons. Photons have no mass. The p equals mv momentum equation can be used for particles with mass. Photons have no mass, so we need to use this equation on the left, the de Broglie wavelength equation. I will rearrange that. P, momentum, equals h over lambda. In this problem, I'm going to do some extra symbolic manipulations just to show you what can be done. Going back to our original wave velocity equation, v equals lambda f, and solving that for lambda, wavelength equals v over f. So if I take that, the v over f, and plug it in for lambda, and do a little bit of rearranging in my head as I go along here, I get p equals h f over v. You'll see that's consistent when I plug in v over f in for lambda there. Likewise, I also have the photon energy equation, E equals hf. If I solve that for f, I get f equals E over h. And once again, if I take that and plug it in for f, and do a little bit of the algebra in my head, you end up with P equals E over V. So this is really an alternate way of solving for the momentum of a photon. Just plug in its energy, divided by the velocity being the speed of light, 3 times 10 to the 8th meters per second. So yes, it's a new equation, but not really a new equation. It's a combination of these 3 equations that haven't already been used. But that will be a shortcut in this problem if you use that particular equation right there directly. This problem is similar to 1 or 2 that we've done in the past. And here's the approach I like. You have individual photons. We're going to find the energy of these individual photons by using, first of all, V equals lambda F, and you're given lambda in this problem, and you're given V. So V is 3 times 10 to the 8th, it's a photon, speed of light, equals 632 times 10 to the negative 9th meters times F. So calculate F, get an answer there. Then you'll calculate the energy of these individual photons by E equals H F. You know H, Planck's constant. F you plug in from the previous part, and you'll have the energy of that photon. I'll just call it E sub photon. Equals some number. Now, on a separate track here, we have power equals energy over time. We want to figure out the total amount of energy involved in this particular situation. I tell you that the power is 1 milliwatt. That's 0.001 watts. That's the power. Equals, I'm going to call this E total, the total energy, over the time. It says you have 1 milliwatt, and we're looking at a 1 second time period for a particular cross-sectional area. So the time is 1 second. So E total is pretty easy here. It's, well, 0.001 joules. That's the total energy. When we know the energy of a photon, how many photons will it take to make that much energy? I'll let you figure that part out.